Okay, Ji, now let's discuss what happens when once data has been transferred. So before this, we were discussing what are the data transmission methods. We discussed packet switching. We discussed serial versus parallel data transmission, simplex, half duplex, full duplex, and synchronous and asynchronous data transmission. We also studied how your wireless data transmission, how your USB data transmissions takes place and how internal circuitry data allows for data transmission. Now, well, that's one problem that we addressed. Now let's talk about what happens when the data transmission has in fact taken place. Are there methods that to ensure that in fact data transmission was carried out properly? And if it wasn't properly carried out, then what steps are involved to make sure that data transmission is again, handled properly so that if I don't have the correct data, I cannot use it further. So what steps are there in place to ensure that correct data transmission and complete data transmission takes place? Now we need to understand that there are two methods here, error checking methods. We're going to be talking about error checking methods, but in fact, there are two error checking methods. And there is one, there is two aspects about error checking. There is error checking only, in which my communicating devices are using methods to simply identify that there is something wrong in the data. What is wrong doesn't know, they don't know, but there is something wrong. And there are methods that allow for error checking and then for error correction as well. Now, one is error checking only. That means is simply identifying that something is wrong. When we go from error checking to error correction, it means that it's also identifying what is wrong. Therefore, it can proceed towards correcting it. Now, we have to discuss some methods over here. Some are error checking, the other are error checking and correction as well. So let's start by discussing first of all parity checking. Okay, parity checking relies on the concept that I have, for example, I'm sending I'm sending bytes of data at a time. The bytes of data include 7 bits of the actual data that is meant to be transferred, and the most significant bit is my parity bit. That's not part of my data, but I will use this to ensure that data transmission is carried out correctly. So my actual data is the remaining 7 bits. My most significant bit will be my parity bit. Now, there is a parity which is even. Parity means number of ones in my whole byte that is being sent. So if my number of ones that are being sent are even, that means it is even parity. If my number of ones that are being sent is odd, that means it's odd parity. Now, whether it is even parity or odd parity, it doesn't matter. What matters is that both sender and receiver agree on the same parity. So if my sender and receiver have agreed on even parity, it means my sender will make sure that the data byte that is being sent has an even number of ones, and the receiver will again check that if the receiving data that has arrived also has an even number of ones. If both devices can agree that yes, you agreed on sending an even number of ones in my data, I received an even number of ones in my data, that means data transmission has been carried out correctly. Otherwise, if there is something wrong, that means that if agreed parity was even, for example, the sender must have sent even number of bits, but during transmission, some error happened due to which my receiver will end up with odd number of bits, odd number of ones, odd number of ones. Because of this, my receiver will understand there is something wrong with the data, and it will simply alert the original sender that I did not receive data correctly. Please retransmit. As you can see here, this is an example of an error checking method, and it's simply identifying that something went wrong. What went wrong, we don't know, but it just identified that something has went wrong. Now, this is the overall principle of what parity checking involves. Parity is predefined, sender and receiver send data and receive data according to that parity. Parity means the total number of ones in the bytes that I'm sending. Even parity means my total data transmission bytes in my total number of ones in that one byte is even. Odd parity means that total number of ones in that byte is odd. Now let's just say this is my data. As you can see here, I already have 1, 2, 3, 4 ones in this one. Now let's just say if even parity was agreed upon between sender and receiver, that means I do not need to add any more ones. It's already even. So what I will do is I will simply add 0 here, and this is my completely fine byte to send according to even parity. However, if agreed parity was odd, in which case using this data, I will have to add another one here to make it odd. That's why for odd parity, I will end up with this value over here. This is my odd parity data transmission. Now, whether it is even parity or odd parity, what's important is that my receiver, sorry, will also receive the same parity. So if I send this data using even parity, my receiver should also have even number of ones. Similarly, if my sender agreed and sender receiver agreed on odd parity and I send this byte, my receiver should also have this exact same byte. Now, there is one very important problem, very big problem with parity checking, and that is that if data transmission is carried out, and if say one bit changed, during data transmission, then my computer, my receiving computer, let's just say, for example, I have right here this bit being sent. This is 1 byte right here. And you notice that it has 1, 0, 1, 1, 0, 1, 1, 0. As you can see here, we have odd number of ones here. 1, 1, 2, 3, 4, 1, 2, yes, odd number of ones. And we got 1, 2, 3, 4, 5 ones here. Let's just see, this is my sender and this is my receiver. Let's just say that only one bit changed. We can say that this bit changed. It became 0. That means my receiver will receive something like this. So what that means is my odd parity is odd number of ones. I think, yes, this is odd number of ones. My receiver, I have changed my 1 bit. This is odd. Sender and receiver agreed upon odd parity. I think I said odd parity. Now, sender and receiver agreed upon odd parity. I have odd number of ones here. I should have odd number of ones at the receiving end too. But what happened is that 1 bit got corrupted. This bit got corrupted. Because of this, my receiver receiving this data right here. As you can see here, my odd number ones have turned into even number of ones. 1, 0, 1, 1, 0, 1. This is even number of ones. Because of this, my receiver will be alerted and it will say that data transmission is not correct because we agreed upon odd parity. I'm receiving even number of ones. That means there's something wrong in this data transmission and please retransmit. So in this case, it's working fine. But what happens when my sender sends the exact same byte using odd parity as agreed upon, and say instead of 1 bit being changed, 2 bits change. Say that this just say this bit changed and this bit changed, or it could be anything else. We can say that this bit changed. So these 2 bits changed, because of which my receiver is now receiving something else. Now I have, instead of 1, this should be 0, but I'm receiving 1 here. Rest is 1, 1, this is 1, this is 1, this is 1, with 1, then 0. And finally, this bit should be 1. I'm receiving 0 here, then 1 and 0. Now you can see here that even though I have changed 2 bits, but my odd parity is still intact. So that means that the error will not go detected. My receiver will say, okay, you said odd parity. I still have odd number of ones here. That means there's nothing wrong. Even though not 1, but 2 bits changed. In which case, there is a very big flaw in my parity checking, that if an even number of bits are changed, again, I repeat, if even number of bits can get changed, 2, 4, 6, if even number of bits get changed, then the parity will remain the same. So instead of, for example, I say I changed 2 bits, let's say I changed 2 more bits, I changed 2 more bits, I changed 2 more bits over here. This will become 0 and 0. Now, because of this 0 and 0, and you notice here, it's still odd. That means if an even number of bits changed, they can come from 0 to 1 or 1 to 0, whatever it is. If an even number of bits changed, that means the parity will remain the same and my receiver will not be able to detect an error. So this is the difference between this is one of the biggest flaws regarding parity. Now, because of this flaw, we have to shift towards another method, okay? Now that method involves the transmission or making use of a parity block. Now, what is a parity block? Parity block means that instead of sending just 1 byte at a time, I send a block of bytes. Because of this, okay, the parity block method goes something like this, that instead of sending just 1 byte, I'm sending a block of bytes. So there's simultaneously sending multiple bytes together. And this is the logical representation of that, what that may look like. It looks like a table, right? So like any table, we have rows and columns. Now, basically, the principle is pretty much the same, that we agree upon a parity. So sender and receiver agree upon either even or odd parity. In this case, in this example right here, we have an even parity. By the way, parity block method is actually an error correction mechanism, that it can identify the bit whether that is wrong, and it can also correct that bit. So therefore correcting the data. Now, as you can see here, this data has been sent to from my sender to my receiver. So instead of just sending 1 byte, I'm sending multiple bytes together. Now, what the receiver will do on receiving this data, it will start identifying where there might be something wrong. Now, how? I repeat, both sender and receiver have agreed upon even parity. So how does parity block method work here? So first of all, I identifies the rows. I look at the rows one by one. In the first row or the first byte, it says byte number 1 here. I will look at the first byte or the first row. I will see is there any byte or row that does not meet even parity criteria. Look in the first row, wait, 1, 2, 3, 4, 5, 6. These are 6 number of ones. So that's even parity. That's fine. Then we have 1, 2, 3, 4. That's also fine. Byte 2 is okay. Then byte 3, 1, 2, 3. So 1, 2, 3, 4, 5, 6. That's also fine. Byte 4 is okay as well. 1, 2. That's fine. Byte 5, 1, 2, 3, 4 is okay. 6 is okay. 7 is okay. 8, there's something wrong with byte. This is why it's highlighted. 8, look at 8. 1, 2, 3, there's something wrong with byte 8. It's not even parity. It's okay. We identified the byte number 8 as being odd parity. That is not agreed upon. This is something wrong with byte 8. Now let's look at this column wise. Column wise identifies the exact bit, right? So starting from top to bottom, we'll do the same procedure, but this time we'll look at the entire row. As you can see here, 1, 2, 3, 4, 5, 6. Okay, this time I have also even number of ones here. Yeah, I have even number of ones here as well. 1, 2, 3, 4. Okay, 4. That's okay. Bit 3 is okay as well. We can start from top to bottom. 1, 2, 3, 4. That's also fine. This is also fine. There's something wrong in bit number 5. How? 1, 2, 3, 4, 5. So even parity is being violated here. It's not even parity. So what that means is that my byte 8 was not following even parity, and my bit 5 is not following even parity. So basically what that means is that bit 5 of my byte 8 is not right. There's something wrong with this. It should not be 1. It should be 0. So in that case, if I solve this problem, if I change this bit back to 0, that means my whole parity block will be adhering to my even parity standards. So I have basically corrected the data. I have narrowed down the exact bit that is wrong, and I have corrected it. I have shifted that 1 to 0. If it was 0, I would shift it back to 1. This is it. This is binary data, 1 and 0, right? If it's not, if it should not be 1, it definitely should be 0. So this is how parity block method works, and it is an error correction method. So I repeat, first of all, you look at the rows or the bytes in this diagram. For example, this table, it's highlighted, there is a byte, and you see which row is not following the agreed parity. And we started from the top, and we ended up at byte 8, and we found out that byte 8 is not following the agreed parity. Once we identified the row or the byte that is not following the agreed parity, we will shift towards the columns. We will start looking at the columns, and we see which column does not follow the agreed parity. In which case we see this was okay, but this column or this bit number, there's something wrong here. This was not agreeing on the agreed parity. This was not following the agreed parity. Because of this, we have narrowed down that this byte or this row and this column, there's something wrong with this bit over here, wherever these 2 points intersect right here. So byte 8, the bit 5 of byte 8 is not right. And that's why we can identify that particular bit and correct it. And this is both parity checking and parity block method.